Alright, welcome back. We're at MECH1340 here. We're getting into Chapter 3, review of number systems and codes. Alright, some of you guys that did digital electronics with me, alright, this should be a lot of review. Hopefully it all comes back to you when we start talking about the different number systems that we're going to go through here. Alright, first one. The one that you and I use every single day. Alright, this is the decimal number system. It's what we use, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the digits that we use, okay? And it's a base 10 numbering system. All right, so it's base 10 because there's 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are our 10 digits that we use with the decimal number system. All right, and you and I use like the number 100, the number 579, right? That's all in our decimal system. All right, but you have to understand the decimal system, right? It's restricted to the digits 0 through 9. That's important because the other systems we have different bases, so they have different digits that are in use. Okay, the other one is going to be the binary system, right? We've done a lot with binary stuff in here already, but remember, binary has a base of 2 because there are only 2 digits in the binary system, right? 0 and 1. For us, it means what? On or off. 0 volts or 5 volts. When we did like all of our stuff in digital electronics where we used our breadboard companions and we wired all that up, right? Our control voltage was 5 volts. When we use the FPGAs, control voltage is 5 volts. When we've done stuff with the Arduino boards, all right, the control voltage was 5 volts. When we work on PLCs and everything, our control voltage is going to be 24 volts. So we will have 0 is still off, right, and 24 volts will still be on. But that's still, in essence, to us is, high and low, true and false, on or off. So you need to start thinking about everything. It is or it is not when we're dealing with stuff in the binary system. Okay, so with the binary systems, okay, we have to make sure that since it's only 2 digits, we're constantly changing and growing and expanding the values. All right, so 0, well, we start out at 0, 0, 0, 1, 1, 0, and 1, 1. Those are the values, all right, that get us 0, 1, 2, and 3 in decimal. Now, I'm going to do some of these charts on the board for you too, and I'll put some separate notes up and online. But like I said, most of this is review, and you're going to see this in a different table. So we're going to increment the least significant bit over and over and over is going to go between 0 and 1, 0 and 1, okay? And then our most significant bit is not going to change as much. So the table is going to look a little bit more like this. All right, if we look at the binary values, now the part on the table, this one's taken from your book. I don't like it because it doesn't show all the values before 0. So it has 0, 1. But it should be like 0, 0, 0, 0, 0, 0, 0, 1. 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, so on and so forth, okay? We should have, a certain number of digits that we have, so the number makes sense that we kind of understand that it's in binary. But there is a subscript that we can put it on it too that has a 2 that's binary, okay? But take a look at these different number systems here. So we have the decimal number system, the one we use every day that we count with, right? We have 10 digits, right? And we can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start over by putting a 1 in front. Okay, so that's how we get 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Now, octal, okay, it's base 8. So octal's base 8. It's going to use 8 digits. Those digits are 0, 1, 2, 3, 4, 5, 6, 7. Then we start by putting a 1 in front of all those. So we have 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and then we start all over, 2, 0, 2, 1. So we're incrementing the most significant bit in front of it. What you need to understand about octal is we don't call that 10 in octal. We call it 10 octal because 10 is only applied to a decimal number. So although it's 8 in decimal, all right, it's 10 octal. Okay, and then hexadecimal, we use 10 digits and then we also use 6 letters. 10 digits and 6 letters because we have 16 places that we need to account for. That equates to the decimal of 0 through 15 in decimal. All right, but hexadecimal, we use all the digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then after 9, we use letters, A, B, C, D, E, and F, where F equates to 15 in decimal. It equates to 1111 in binary, and it equates to 0.17 in octal, okay? And we'll go through being able to go back and forth between octal, hexadecimal, binary, and that sort of thing, okay? So this is converting a binary number to a decimal number. So how do we know it's binary? All right, so it's 10101101, and then that subscript of a 2 tells us that's a binary number. Because that number, could be a decimal number, as well if we take a look at it, right? It'd be 10 million and something. But we have to know that it's not 10 million and something and that it's a binary number, so that subscript 2 after it tells us it's binary. All right, so since binary is base 2, we're going to go up by multiplying by the base. So, and we're going to go from right to left. So the letters in pink at the very top, okay, those are the exponents that we're going to put on the base as we go right to left. So you'll notice we'll go 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th when we do this. So what we do is we take that binary number and we multiply it by the base to whatever power needs to go there. So the first one is going to be 1 times 2 to the 0. 2 to the 0 is 1, so 1 times 1 is 1. And then eventually when you get good at this, you can ignore the zeros. But in the next case, we have to take 0 times 2 to the 1st. All right, 2 to the 1st is 2, 0 times 2 is 0. Then we do the next value. We have 1 times 2 squared, so it's 1 times 4, which is 4. Then we have 1 times 2 cubed, so it's 1 times 8, which is 8. Then it's 0 times 2 to the 4th, so it's going to be 0 times 16, which is 0. And then it's going to be 1 times 2 to the 5th, so 1 times 32. Alright, it's 32. And then it's 0 times 2 to the 6th, which is 64. So we get 0 times 64, which is 0. And then we have 1 times 2 to the 7th, which is 128. 1 times 128 is 128. Now, some of you might just want to take the shortcut approach and know that we're going to multiply by 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. It's going to double each time. Why? It's binary because the base is 2. So if you learn that pattern as well, it'll also work. So what do you do once you've done all the multiplying? You add them all up. So 1 plus 4 plus 8 plus 32 plus 128 gives us 173. And then we write the subscript 10 so that we know that it's a decimal number. So this is how we convert from binary to decimal. Okay? Binary to decimal. So all your homework problems, just make sure that you have all this written down. You're able to kind of follow the pattern. There's a couple different ways you can approach this, all right? Just get comfortable with the one that you understand. If you have questions on this, like I said, don't hesitate to email me, or we can do some over like a Zoom or Teams call as well, okay? And you've heard me mention before the most significant bit and the least significant bit. Remember, the least significant bit's the one that's going to change all the time. So the one that's constantly going 0, 1, 0, 1, 0, 1. The MSB, the most significant bit, that's always the leftmost bit. All right, and it's always the one doing the place holding. Okay, so in the number 0001, the 1 is the LSB, a 0 is the MSB on the right hand side. If I have the number 1000, the 1 is the MSB, and then the 0 on the right hand side is the LSB. Okay, so each word is 16 bits. Okay, just so we know, we've covered some of this in the previous lecture as well. Okay, and a group of 8 bits is called a byte. Okay, so we can even distinguish between the lower byte and the upper byte when we're talking about characters. Okay, so if memory size is 1 kilobyte word, or kilobyte, sorry, not kilowatt, it can store 1028 words or 16,384 bits of information. So when we start talking about streaming things, all right, we're streaming bits of data. This is really what we're talking about, is streaming a bunch of ones and zeros through the system and how we store memory and all those different things. Okay? All right, let's do the next part. We want to go decimal to binary. So this is where we have to use what we call successive division by 2, and then when you write your answer out, you have to write it from bottom to top when you get this, from MSB to LSB. So successive division by 2. So we're going to take the number 47 and convert it to binary. So we're going to take 47 divided by 2. The closest we can get is 23, right? 23 times 2 is 46. So we're left with the remainder of 1. Then we take the number 23 and divide it by 2. The closest we can get is 11, right? And 11 times 2 is 22, so we have a remainder of 1. And we write down all the remainders over there on the side. Then we take 11 divided by 2, we get 5, and we have a remainder of 1, right? Because 5 times 2 is 10, 11 minus 10 is 1, so we still have a remainder. And then we take 5 and divide it by 2, and you get 2, right? 2 times 2 is 4, so we still have a remainder of 1. And we take 2 divided by 2, and we get 1, so we have a remainder of 0. And don't forget to do the last step. We have to take 1 divided by 2, goes in 0 times, so we have a remainder of 1. So once we've done all this out, we have to write the number from our most significant bit to our least significant bit. If you write it backwards, okay, you're going to be incorrect. So we have to write this out as 101111. All right, so there's how we go from a decimal to a binary number. Okay, so we can take a look at how it's addressed. Okay, so computer memory looks like something, maybe like this for like 16 bits. Okay, so it's made up of single bits that we group into 16 words, and each address is going to carry a string of bits there. So remember, this is Allen Bradley, so that's why it's O:1, O:2 for output 1, output 2, output 3. Okay, so that's just Allen Bradley addressing. It'd be a little bit different for us with our Siemens. Okay, remember, for us, each bit here, 0 is off, 1 is on. So there's how we would send through a word. Remember, a word is 16 bits, and in decimal for us, that's 0 to 15, but it's really just a string of ones and zeros as your computer sees it. All right, how do we handle negative numbers? Okay, so, and this is sometimes, just a test question and things like that. So binary numbers, we can't say like, plus 10 or negative 10. It doesn't work that way for us. All right, so in the binary number system, if the MSB is a 0, and this is only when we're talking about signed numbers. All right, so it's very specific to when we're adding and subtracting and doing those sort of things. It doesn't mean in the realm of things, if I have the number 111, that it's -7. The number 111 is really 15 when we're counting. But you have to remember that we use binary numbers for different types of things. All right, so when we are adding and subtracting and having signed numbers, okay, we use the MSB as 0. If the MSB is a 0, we have a positive decimal value. If the MSB is a 1, we will have a negative decimal value. That's really, the best way for us to keep track of this, okay? So the leftmost bit is really the MSB, all right? And MSB necessarily, that's more for counting and things like that. So you can take a look. The leftmost bit, if it's a 1, we have a negative decimal number. If it's a 0, we have a positive decimal number. And then they increment upwards, okay? So that shouldn't be too bad. I know there's a couple test questions on positive and negative numbers, just so you know. Okay, we also express them in another way. There's a couple other ways we're going to do. There's the ones complement and the twos complement. The ones complement, okay, and we're going to get into how we add, and what is the significance? We're going to get into how we add and subtract these numbers, okay? So in order for us to subtract binary numbers, we need to understand how to use the ones complement or the twos complement so that we know how to correctly subtract numbers by adding the negative number to it, if that makes sense, okay? So we're going to get to that at the end of this lecture, but for the first part, we need to understand how do we get a ones complement. We get a ones complement number by changing all the values. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. Okay, so if we look at our original binary number here that's all zeros, its ones complement will be all ones. All right, and you shift every single digit. So if we look at the second example there, the one that's 000000001, notice its ones complement is 11111110. Notice how we switch. If it's a 0, it became a 1. If it's a 1, it became a 0. That's all you're doing for taking the ones complement. we're going to use the ones complement later, right? Because it makes it a negative number for us to add and subtract numbers. Okay, 2's complement is very simple. We take the ones complement and add 1 to it. Okay, so we take the ones complement of a number and then we add 1 to it. I'll show you how to add a little later in the lecture, but that's what the 2's complement is. So you take the ones complement of a number, then you add 1 to it. So remember, a 0 in front indicates a positive, a 1 in front indicates a negative number. Alright, so let's talk about the octal system here. Octal system has a base 8. So I briefly touched on a little bit ago when we were looking at the table. Alright, so octal uses 8 bits, which are the digits 0, 1, 2, 3, 4, 5, 6, 7. You do not allow 8 and 9 in the octal numbering system. So if you see the number 8 or 9 and someone's telling you it's octal, it can't be, because it's not possible, because we don't use the digits 8 and 9 in the octal system. Then we repeat, right? So 0, 1, 2, 3, 4, 5, 6, 7. Then we get 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Then we start over, 2, 0, 2, 1. Remember, we don't call that like 10, 11, 12, 13 when we're doing octal. You have to say it's 1, 0 octal, 1, 1 octal. It is not 10 octal, 11 octal, okay? Don't say it that way. Those numbers only mean something to us as decimal. Alright, so the octal number system, right? The base is 8, okay? So PLC controllers, right? We use more of an octal system because every slot, and you're going to learn this as we program, has the addresses, you know. So if we're talking about slot or rack 0, right? And then we say the slot number. So it would be 0, 0, 0, 1. 0, 2, 0, 0.3, 0, 0.4, 0, 0.5, 0, 0.6, 0, 0.7. And then we move on to the next one. So it'd be like I. And then it would be, you know, 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. All PLCs, regardless of brand, Siemens, Allen Bradley, Mitsubishi, any of those, okay? All are set up the exact same way when we do that. All right. So let's learn how to convert some numbers here. So we want to be able to go octal to binary. Okay, you can either understand your table or understand this. It's the same procedure from when we went binary to decimal. Only the one thing that changes, right, is now we have the base is 8 instead of 2. Okay, so it's going to be 8 to the 0, 8 to the first, 8 to the second, 8 to the third, 8 to the fourth, 8 to the fifth, right? So on and so forth, however many octal numbers we have. Alright, so I'm going to take 2 times 8 to the 0. 8 to the 0 is 1, so 2 times 1 is 2. Then I'm going to take 6 times 8 to the first, right? Remember, it's octal, so it's base 8. So 6 times 8 is 48. And then I'm going to take 4 times 8 squared, which is 4 times 64. Alright, so that's going to give me 256. And then I sum all those up. So 2 plus 48 plus 256 ends up giving us 306. And that subscript 10 means that it is a binary number. Alright, so this is converting an octal number to a decimal number. Alright, we'll have some homework problems on this. Now, we can convert octal to binary a little bit easier just using the table. Okay, so if we have this octal number 4, 6, and 2, 4, 6, and 2, the number 2 is 0, 1, 0 in binary. It's 1, 1, 0 is the number 6 in binary, and 1, 0, 0 is the number 4 in binary, and then we can stick all those together. It's imperative, okay, that we're using 2 to the third here, right, which is 8. So since it's 2 to the third, that means we have to group them in chunks of 3. So that's why you see it as 0, 1, 0, that's a chunk of 3. 1, 1, 0 is a chunk of 3. And 1, 0, 0 is a chunk of 3. Okay, because 2 to the third is 8. 8 is significant because 8 is octal. So that's a shortcut there to go from an octal to a binary number. So the full binary number would be all of those put together into one string. So it would read 1, 0, 0, 1, 1, 0, 0, 1, 0, all as one string. Okay? The hexadecimal number. All the concepts are going to be the same. It's set for hex's base 16. So we're going to use the digits 0 through 9, and I've already touched on this. And then we're going to use the letters A through F. And then we repeat. Okay, so after that, you would have, incrementing what's in front. So 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1 A, 1 B, 1 C, 1 D, 1 E, 1 F. Start over with a 2 in front. Okay, so that's a hexadecimal numbering system, base 16. So, same concept. We want to go hexadecimal, but now hexadecimal base is 16. So the math step's still the same. All right, we're just using 16. So it's going to be 7 times 16 to the 0. So it'll be 7 times 1, which is 7. Then we're going to get B times 16 to the first. B is equivalent to decimal 11. So we're going to take 11 times 16 to the first. So 11 times 16 is 176. And then we're going to take 1 times 16 squared. So it'll be 1 times 256, which is 256. And then we need to sum all of those together. All right, so we're going to get 7 plus 176 plus 256. That's going to equal 439 in decimal, still keeping the subscript 10 there to know that that's a decimal number as we go through this. Okay, so like I said, the concept is the same for converting anything to a decimal. You just have to keep track of what base you're coming from. So we're coming from hexadecimal here to decimal, so we got to use base 16. Okay, then going hex to binary is almost just like going octal to binary, only in hex we have to group it in numbers or in strings of 4. So the number 7 in binary is written out as 0, 1, 1, 1. Okay, B in binary, right? Remember that's what? The number 11 in decimal, which is equivalent to 1, 0, 1, 1 in binary. And then the number 1 in binary is written out as 0, 0, 0, 1. Right? We're keeping each one of those in chunks of 4 because it's a hexadecimal number. 2 to the 4th is 16. So that's why it's a base 2, right? 1s and 0s. And to the 4th, so 2 to the 4th is 16. That makes it hexadecimal. That's why we have to chunk these in groups of 4 when we write out this long string of 0s and 1s. Okay, so remember in this case, the most significant bit is the 0 all the way on the left. The least significant bit is the 1 all the way on the right. Okay. Binary coded decimals. So now we can take, strings of binary numbers and code them a little bit differently. So, now you start talking about 256-bit encryption or 512-bit encryption or 128-bit encryption. Those kind of numbers should start ringing a bell here, okay? So we can do a binary coded decimal, and, you see what the table brings here. So we use the 4 bits to store in the values. So it's almost hexadecimal for the most part, but it's a binary coded decimal. So you can see, and you're going to use the table. So I would make sure that you guys have complete tables out when you're doing homework. Okay, as you notice, all right, it's kind of like going, hex to binary almost. All right, so we have this decimal number here, and this is a binary coded decimal. So this should be pretty easy. So since it's a BCD, the number 3 in binary is 0011. The number 6 in binary is 0110. The number 8 in binary is 1000, and the number 7 in binary is 0111. So we take all those, the entire string, and put it all together as one big binary number. Okay, so that's a binary coded decimal. Kind of similar it's really similar as going from hex to binary. Same kind of concept, only we're taking a decimal number and we're encoding that decimal number as a binary number when we do that. So that's why it's binary coded decimal as we go through this. Okay, so, and how do we know? All right, it looks a little bit different. So we have to be able to distinguish between a binary coded decimal or a binary number. So notice, if we took the decimal number 49 and expressed it in binary, that's where we would have to take 49 and do successive division by 2. If we did that, it came out to be 110001, and that's in binary. If we do a decimal 49 okay, expressed in binary coded decimal, we would rewrite 9 in binary, that's the 1001, and we would rewrite 4 in binary, okay, and that's 0100, and then we would put those together. So you can see the difference between if we have 49 decimal as a binary number or 49 decimal as a binary coded decimal. Okay, that's really kind of the difference between the two. Okay, we can also use a thumbwheel switch. All right, so that's just where we're kind of rolling it along. Okay, and it changes our value, and it's a binary coded decimal. So that's, you don't use too many of these anymore, but you do see them occasionally. Okay, so what really happens here, right? We take that thumbwheel and we set the specific number we're looking for. So it takes the input, it takes the binary coded decimal to binary, processes it through the PLC, and then it goes binary to binary coded decimal and gives us a decimal readout. So we can go through and convert everything based on addresses. Okay. So what we can do is, when you guys do your PLCs, one of the formats that can have you change. Now this is on an Allen Bradley, but Siemens will do the same thing. You can take a look at the output table, and we can make that output table display a binary value, an octal value, a decimal, or a binary coded decimal as the output, so that you can look at the data as it's processing through. All right, next up is the gray code. Okay, so what's the gray code for? It's more for encoder circuits and things like that, because the gray code's a little bit different. It's not like we're counting in binary. It's about 1 bit changing at a time. So your hard drives do this, DVDs, CDs, those sort of things do this. It's very confusing for counting, but we use it for encoder circuits. So circuits that we, even if we want to keep track of how far something moves or things like that. Okay, it gives us much more accurate controls of motions of robots. So your servo motors use kind of some gray codes so that you have a position encoding. So there's much more error minimization there. So it kind of makes sense if you look at this encoder disk. This uses 4-bit gray code, so you can kind of see how it's written. And as the outermost part of the rim, okay, that's going to be the most significant bit, where the inner part of the rim is the least significant bit. So as this disk rotates around and as the laser moves back and forth, you're able to use the gray code to understand what's going on there. All right, the ASCII code. Okay, now this is for your keyboard. All right, so everybody kind of wonders, when you punch a button on your keyboard, what does it mean? So if we want a capital A, okay, in order for us, when you hit like Shift A and put out a capital A on your screen, it sends out the 7-bit code of 10000001. So there's a huge code, all right, and these are the standard code for information changes, but this is what your keyboard's doing. So when you press a button on your keyboard, it puts out this 7-bit code, and then that's translated, and that's what's displayed on your screen. So there's how we, present letters and numbers and all kinds of different symbols and things like that on your screen. Every single one of those has a certain binary or a certain number of bits associated with it for it to be able to display on your screen. So when you're typing, you're hitting those, you're literally just hitting a bunch of ones and zeros and displaying them on the screen. Okay, so every keystroke goes through this. Now this interface, this is a little old school on the computer here, okay? But now that we use USB drives and things like that, or we use wireless transmission through USB as well, because USB is much faster than our serial ports from before. But that's really what's going on. And why were they limited to 7 bits? Because of the kind of plugs that we originally had. All right, they could only handle certain transmission of data at a time when you type a code. So that's why nothing's really changed about what the codes are for the letters. All right, we've kept that the same, so a lot of things don't have to change. But that was kind of one of the restrictions that was put on it. All right, let's talk about parity bits now. So we check the accuracy of data. All right, so we know if something changed from a 1 to a 0 or 0 to 1, we can use a parity bit to detect errors that occur when like a word is moving. All right, so we should know if it's, there's two different types of parity that we're going to take a look at. Okay, there's even parity or an odd. It just kind of depends on how we, set everything up and we talk about it. But eventually, you're checking to see if something is even or odd, and that'll let us know if there was an error involved. Okay, so if we take a look, and you don't look and try and compare the even and odd at the same time. We either, focus on doing strictly odd parity or strictly even parity when we do this. Okay, so our parity bit could be a 0 or it could be a 1, depending on the number of 1s and 0s. Alright, so if we have odd parity, means that the total number of binary 1 bits in the character, including the parity bit, is odd. Okay, so cover up the even parity here. So what does that mean? If we look at and we start counting the original character. So once again, we're covering up the even parity, we're just looking at odd. So we look at the original character. So the original character of 000 was sent in. Okay, we want to count up the number of binary ones. Well, since there aren't any binary ones in that number, okay, and they're not odd, we would put an output parity bit of a 1. Let's look at the next character. We have 0001. We count the number of ones. There's one number of ones. 1 is an odd number, so we would send out a 0 for the odd parity bit. Let's look at the next character. We have 0010. We count the number of ones in that character. There's 1. That means it's odd. Since there's an odd number of characters, we output a 0 for the odd parity bit. Let's look at the next character. We have 0011. We count the number of ones. Now there's 2 ones. That means there's not an odd number of ones, so we have to put an odd parity bit of a 1 as an output. Does that make sense? All you're doing is counting the number of ones. We're strictly talking odd parity right now, not even parity. We're strictly counting the number of ones. If the number of ones is even, our odd parity output will be a 1. If the number of ones is odd, our output for our odd parity bit will be a 0. Okay? Now, even parity, same kind of concept. So let's take a look. We're covering up the odd parity bit part of the table here, and we're just going to look at the evens. Okay, so we're going to count things up. So if we look, let's look at the character 010, and we count the number of ones. The number of ones there's only 1. They are not even, so we're going to output a 1. If we look at the next one, the next character 0011. We count the number of ones, there's 2. So it's even, so we send out a 0. Does that make sense? So even and odd are going to send out the opposite values there. Okay? That's really what's going to go on there. So anytime that there's an even number of ones in the even parity bit, we will send out a 0. If there is an odd number of ones when we're doing even parity, we will send out a 1 signal. Okay? So there's understanding even and odd and how we encode that so that we can take a look and see. Alright, so in the first scenario here, if we send through 7 bits of data and they're all zeros, the number of 1 bits is a 0. So the last bit on our parity would be 0 for an even and 1 for an odd. So we would send through, you have 7 bits of data, alright, and then we would actually send through 8 bits of data, and the last bit's a parity bit. So let's look at the second 7-bit of data sample. If we count the number of ones, there's 3 ones there. So since that's odd, okay, that's an odd number of ones, our even, the last digit on our even would be a 1, the last digit on our odd would be a 0. Look at the next scenario. We have 11010001. There are 4 1 bits there. That's even, right? There's an even number of ones. So on our even parity, our last digit would be a 0. On our odd parity, our last digit would be a 1. Okay, so hopefully that's starting to sink in. I'm not going to spend tons of time about us understanding even and odd parity, but alright, we just use it to check through codes and make sure that data is valid. as it comes through, okay? And we can do it and use comparators and make sure that works later. All right, so let's get into some binary arithmetic. So yes, we can add and subtract numbers in binary. So we do this, all right, and we take 0 plus 0 is 0, 1 plus 0 is 1, and 0 plus 1 is 1. And now the last one's the most important one because the other three are very simple. This one you got to pay attention, all right? 1 plus 1 is 0 with a carry 1. What does that mean? Well, in our world, 1 plus 1 is 2, right? Well, what's 2 in binary? 2 in binary is 1, 0. Notice the 1 for that is our carry bit, all right? And the 0 is our LSB, our placeholder. So 1 plus 1 isn't 0. It's 1, 0, but that 1 is a carry bit. So 1 plus 1 is still 2. 2 in the form of 1, 0, and our 1 is in form of a carry, okay? So let's take a look here at how we do some addition. So if we take the number 5 plus 2 in decimal, we know 5 plus 2 is 7. Now, if we take, the equivalent, 101 is 5 in binary, and 010 is 2 in binary. So if we add these together, you add just like old school math. 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 0 is 1, so we would get 1, 1, 1. You only carry if we have 1 plus 1, or if we have 1 plus 1 plus 1, right? For us, decimal, 1 plus 1 plus 1 is 3. Binary, 1 plus 1 plus 1 is what? 1 plus a carry of a 1, because we have to get to 1, 1, which equals 3 in binary, okay? And this is an example of that. So, with that, we have 10 plus 3 is 13 in decimal, right? We know how to do that. But 10 in binary is 1010. 3 in binary is 0011. So when we add these together, all right, we get 0 plus 1 is 1. Then we get 1 plus 1 is 0 with our carry of a 1. So now we have that 1 bit that's carried over the 0, and then we add them. That 1 plus 0 is 1, okay? And then we add our last one, 1 plus 0 is 1. So we end up getting 1101, which is our binary equivalent of 13. So you just got to remember how to carry. So when are we going to carry? What are our scenarios? If we have a 1 plus 1, we're going to carry a 1. And if we have a 1 plus 1 plus 1, we'll carry a 1 as well. Okay? So here's another example of using the carry bit. If we have 26 plus 12, all right, 26 is 11010, 12 is 01100. Notice I'm putting a 0 in front so that we have the right number of placeholders. Okay, but you should be able to add here and see when we have the carry bit and when it's necessary and how to apply it. So we have 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is a 0 with a carry. So then we get another one, right? We have 1 plus 1, which is 0 with one more carry, and that carry is 1 plus 0, which brings us down to 1. So our final answer is 38, which is equivalent to 100110. Okay? Adding, relatively easy. If we want to subtract, okay, it's a little bit harder for us to borrow when we're subtracting. Okay, so instead of subtracting, we're going to learn to use the ones complement or the twos complement when we do this. Okay, so I'm going to skip forward just a little bit so that we understand how to do this. When we add and subtract, so here is the ones complement method. Okay, so for us, if we have decimal of 10 minus 6, we know the answer is 4. Well, our binary in decimal form is 1010, and minus 6 is 0111. So what we have to do is only the bottom number, okay, because that's the one we're subtracting from. We take the ones complement of the bottom number. So the ones complement of 0110 is 1001, and we add it to the top number. So now we have to do 1010 plus 1001. Hopefully you're with me here. So all we've done is we've taken the ones complement of 6. Because what do we have to do? We're going to take that negative number and make it positive and add. Okay? So when we add that number, we add 1010 plus 1001, we get 10011. Okay? When we did this math, there was a carry at the end. If there's a carry at the end, we have to add 1. So that's what that add 1 is. There's rules to this, okay? So we have to make sure we know the rules. So when we're using the ones complement, if there's a carry at the end, when you do the very last step of your addition, you add 1 to the final answer, and then that will be your result. So we don't use the carry bit in the answer. We bring it down, and so we're really going to take 0, 0, 1, 1, plus 1, and we get 1, 0, 0. You don't carry that 1 down. We're using the end around carry, so that last bit is going to end around. So when there's a carry at the end of the result, we're going to get a positive number. When there's no carry at the end of the result, it's negative, and we have to use a minus sign. So that's a rule that you need to write, that entire paragraph at the bottom there. You need to write that down. When you're using the ones complement to do subtraction, you need to hold true to that rule. Okay? If there's a carry at the end, you add 1 and it's positive. If there's no carry, you don't do anything and you put a minus sign in front of it. Okay? Now, when there's no carry, right? I just said that negative. So here's another example here. All right? If we subtract 1, 1, 0, 1, 1 from 0, 1, 1, 0, 1, we're going to take the the ones complement of 1, 1, 0, 1, 1. So that's what becomes 0, 0, 1, 0, 0. That's the ones complement. And then we add them, right? So 1 plus 0 is 1, 0 plus 0 is 0. 1 plus 1 is 0 with a carry. Then we have 1 plus 1 plus 0 is 0 with a carry. And then we have 1 plus 0 plus 0 is 1. Notice there's no carry at the end that carries over. Since there's no carry for this number, okay, what we're going to do is take the ones complement and put a minus sign in front. So this is the other rule. So there's two rules here. So the one back here that we did first, okay, when we do this, we take the ones complement, add it to the top number, and if there's a carry, we add the 1 around, and that's our value and it's positive. If there's no carry, you have to take the ones complement of that existing number that you get and put a 0 in front. Okay, so those are the two rules that you're going to use for using the ones complement to do subtraction. Okay, if we use the twos complement, okay, you remember to do the twos complement, you take the ones complement of a number, add 1 to it. So we're going to take and subtract 101 from 111. So the twos complement of 101 means that we have to take 101 and do the ones complement, which gives us 010, and then we add 1 to that. So 010 plus 1 gives us 011. So the 011 is the twos complement of 101. Now we can add these together. So we have 111 plus 011, which yields 1010. Okay? So when we're adding these, we ended up with a carry at the end. So since this is a twos complement, the first one indicates that the result is positive, so it is disregarded, and that is the answer. So when we use the twos complement, if there's a 1 in front, we disregard it, assume it's positive, okay? And our answer is just 101. So this is the rule that you need to write. Okay, when we are using the twos complement for subtraction, all right, and we're not talking about it, even if there's a carry at the end. When you get that final number at the end, if there's a 1 in front, you disregard it, and the number is positive, and the solution is 010. Okay. Now, if there's no carry on the last step, the result is negative, and therefore we have to subtract out another 1 there by taking the ones complement. Or you can just take the ones complement and add 1 to it and get the same result. Okay? So that's the other rule. Okay? So what you have to do is add 1 back to it when you do that. Okay? I'll do a couple more examples probably in class to help you guys clarify on that. There's not too many problems that we're going to do where you have to subtract. So just make sure you understand how to use the ones complement or the twos complement rules when we do this. Alright, multiplying just like old school multiplication, like you learned back in elementary school. So literally just holding places. So when we do this and you take 101 times 110, alright, you're going to take that the 0 and multiply it by 101, and you get 0, 0, 0. And then we have our placeholder. All right, so you'll have a 0 down there, and then we take that middle 1 times 101. So 1 times 1 is 0, or 1 times 1 is 1. 0 times 1 is 0, and 1 times 1 is 1. So that's really what you just need to know. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0, and 1 times 1 is 1. All right, and then the last step on this problem, 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. And then you literally just add those all up at the end. Okay? We don't have to worry about carry conditions or anything like that, because that will yield the final answer. All right, so I'm not going to spend a ton of time on that. That's just old school multiplication. Same with division. All right, it's just old school division. You should know how to do this. All right, just break it down into chunks, right? So if we do this, if we're going to take 1110 and divide it by 10, so we're taking a decimal, it's 14 divided by 2, right? But you have to break it into chunks. So you're going to say, how many times does 10 go into just the 1, 1? Well, it goes in once, right? So then you have 10 minus 1, or you have 1, 1 minus 10, which gives 1. You bring down the next 1. So now you ask yourself again, how many times does 10 go into 1, 1? Once, right? So then we have 1, 1 minus 10, and we know that that yields a 1. Okay? Then you ask yourself, how many times does 10 go into 10? Well, it goes in one time, and then you multiply it and subtract it, so 10 minus 10 is 0. It's just old school long division. Hopefully you guys remember how to do that. I might do 1 or 2 more examples in class for you if you guys are struggling on that one at all. But it should be pretty basic on the multiplying and dividing. I think the hardest part is doing the subtraction and being able to use the 1 and 2's complement to do the subtraction for you guys. All right, very last thing just want to talk about is if we use a comparator, all right, and how we use comparators in words and things like that. So we will be able to do some of this in your PLC programming, but we do have a comparator. So we do say, hey, A equals B, all right? Or we can say A is greater than B, or A is less than B. So sometimes we have to do a device or do certain loops. This helps with loops program and things like that. You guys remember that we did this in the robotics class, where we programmed the robot to come down and do like your circle or your square, your triangle, like 5 or 6 times. So we wrote that into the code. You know, as long as this register value was less than 5, it would continue to do your triangle program, and then we would increment the register, all right, and then it would stop when we end. Same kind of concept on that as well. All right, guys. Well, that is the end of chapter 3. This one was kind of a lengthy one, but as usual, email me if you have any questions or let me know. Else, guys, have a great day. I'll see you in class.